So my name is Parsa Ghaffari. I'm CEO and founder at Alien. And today I'm going to tell you a little bit about our company as well as a new embedding model that we've been working on called byte2vec. So in a nutshell, we solve the problem of analyzing and understanding textual and visual content for developers and data scientists. And we're essentially solving two problems that we face when dealing with content. The first problem is the natural and inherent complexity of textual and visual information. So, for instance, in case of text, even in a message that is only a few characters long, you have lots of nuances and noise and abbreviations and so on. So, as a human being, when you read this, you quickly realize that this is talking about the Facebook Messenger app, and the tone is negative, the language is informal. English, obviously, and so on and so forth. And the same could be said about images. Within a fraction of a second, as a human, you can sort of identify all the different objects and their geospatial orientation and so on and so forth. But it's much harder, obviously, for a computer to do the same. So understanding language and vision is difficult, but it's at the core of many user and content-centric processes. And the second problem that we're trying to solve is one of scale. So there's simply too much content out there, and it's growing like crazy, and it's not going to stop. And as Condé Nast recently reported, more content was uploaded yesterday than any one human could consume in their entire lifetime. So whatever solution we come up with for content analysis must be able to scale up to billions of pieces of content per day or so. At a glance, we are 13 people based in Dublin, Ireland. We're a mix of scientists, engineers, and sales and marketing people. We have about 15,000 users on our platform, which collectively pay us tens of thousands of dollars per month to use our services. And then we've raised just over $1 million in venture funding so far. In terms of products, we have two products, both of which are APIs. We have a text analysis API, which is a package of about 14 different functions for extracting different types of information from a piece of text. And then we have our news API, which is an application of that text analysis technology to real-time streams of news content. In terms of delivery, they're delivered either over the cloud or in an on-prem fashion. We have SDKs for 7 different programming languages, and we have integrations and bindings for various data analytics platforms, such as RapidMiner, and more easy to use interfaces like Google Spreadsheets and so on. Just a brief overview of some of the functions that we have in the text API. So sentiment analysis with different variations. We have document level sentiment, aspect-based sentiment, and entity level, which I'll tell you more about in a bit. We have categorization, so categorizing a piece of text according to the topics that are mentioned in it and so on. Entity extraction, finding mentions of people, places, companies, and so on in a piece of text. Summarization, automatically summarizing a piece of text. Article extraction, image tagging, and so on. To give you a high-level idea of how the API works, let's review some basic examples. So with categorization, we have a piece of text. So it says Tesla beats expectations with the new Model S. We specify the language and we select the taxonomy. So we have support for multiple industry specific taxonomies. And in this case, I'm using IABQAG, which is an ad tech taxonomy. And I want to categorize this piece of text. And it comes back with a first and second tier label for me. And it says it's about the automotive industry and electric vehicles specifically. And then in terms of sentiment analysis, we have 3 variants. As I mentioned, we have document level, aspect-based, and entity level. The basic idea is that you have a message, you have a tweet, a comment, a review, and you want to know if it's positive or negative, either as a whole or towards each of the entities that are mentioned in it or towards each of the aspects of the category of service or product that it's talking about. And then entity extraction is another well-known task in NLP. So we have a sentence like Apple was founded by Steve Jobs, and we want to identify mentions of people, places, organizations, and so on. So the first task is to sort of spot those entities and and assign a type to them. So is this a person? Is it a company? And then the second task is to link it to potentially link it to a knowledge base, such as Wikipedia or DBpedia. And that's when you need to perform disambiguation based on the context. So Apple the fruit versus Apple the company. Some of the things that we're working on right now, so we're adding support for more human languages, and as I'll explain later, we're becoming less and less language dependent. So that's that. We're adding Scandinavian languages, Russian, Arabic, Chinese, and Korean and Japanese in the next month or so. Then I think the second thing is allowing our users to adjust the behavior of the API and the models based on their own data. That's something we get asked for a lot. So we're opening up some of the tools that we've built for training categorization and entity extraction models. And thirdly, we're launching more vertical and domain-specific models for tasks such as aspect-based sentiment analysis or categorization. Just briefly about the news API. So it some of the use cases and features that we have here: media monitoring mentions of a company across various channels. Then profiling authors for, say, semantics, so authorship attribution and authorship analysis, trying to sort of build a footprint for, say, each journalist out there or each user on social media. Influencership analysis, which is a combination of the authorship profile as well as some metrics that indicate influence across different channels. And then we have a couple other functions for detecting trends, making predictions, semantic search, and so on. Just a quick example with the news API. So, this is the demo on our website. You can set filters based on keywords with like Boolean search options. You can set a category, so say, give me all the stories that are about electric vehicles, and mention Tesla as a company with a positive sentiment, and you can set a time frame and different source metrics, language, and so on. And it comes back with the analyze and enrich news content. So this is a story from the Business Insider. It has tracked the performance on social media. That's what you see on the first line, and then an automatically generated summary of the article. Then you have the category. So this is about electric vehicles again. These are the entities that are mentioned in it, and the sentiment, the overall sentiment is positive. And then it also provides you with insights and predictions. So various time series for volume of stories that mention this or match this query, average sentiment polarity over time, and so on. Word clouds based on entities, keywords, and so on, breakdown of topics and categories and sentiment, and finally histograms as well. Some of the new stuff that we're adding to our news API, so it's obviously powered by our own text analysis technology, so whatever we add there in terms of domain-specific models or new languages is going to be reflected here. More predictive analytics, more sources, and a more advanced query language are some of the things that we're adding to the news API. And so, as I mentioned, I want to focus a little bit more on one of the major functions of our text API, being sentiment analysis, which essentially deals with quantifying people's opinions and thoughts. And it can be applied to tweets, reviews, or any kind of user feedback, really, textual user feedback. And so you can look at sentiment at different levels, and I'm going to explain the three variations that we have in our APIs. So the most basic one is done at document level. So you have a tweet, and you want to know if it's positive, neutral, or negative. That's the classical example of sentiment analysis. And then you have aspect-based sentiment, where, say, you have a review about a hotel, and you want to know what aspects are mentioned positively and which aspects are mentioned negatively. So for instance here, it says on arrival, staff could not have been more helpful, food was fantastic, the place was spotless. So this, the first three aspects, staff, food, and cleanliness, are extracted from this sentence and the sentiment. And then the second sentence says, the only letdown was the bed was like trying to sleep on a concrete floor, it ruined our stay, sorry. So that's obviously talking about the beds, and it seems to be negative. So that's aspect-based sentiment. We have domain-specific models here for hotels, restaurants, cars, airlines, and so on. Then the third variation is entity-level sentiment. So you want to sort of understand the sentiment towards each of the entities that are mentioned in a piece of text. So Apple easily tops Google, Microsoft in list of valuable brands. 3 entities are mentioned here, all of which are companies or organizations, and then the sentiment seems to be positive towards Apple and slightly negative towards Google and Microsoft. So that's the aim of entity-level sentiment analysis. You can run a 2-step process to detect entities first, and then sentiment, or you can actually run an end-to-end process that learns both jointly. In terms of approach, so one of the key business requirements for us is for our algorithms to be as language agnostic as possible. So in terms of architectures, we use mostly CNNs, LSTMs and variations, and several attention mechanisms. We use word and character inputs for our models. We use distance supervision wherever possible. So in case of, I don't know, Twitter sentiment, we look at emoticons and emojis and so on to collect lots of weakly annotated data. And in case of reviews, we look at star ratings and things like that. So any weak annotation that we can retrieve for cheap, essentially. And then we use pre-trained embeddings, which I'll talk about in more depth later. And finally, we've completely switched our backend to TensorFlow. But as I mentioned, one key area that I would like to focus on is word embeddings. For those of you who aren't familiar with word embeddings, they're essentially these dense vector representations of words, regardless of how they're trained. So meaning essentially you're encoding each word as a set of digits. So for instance, these 100 digits represent the word mother, and these 100 digits represent the word father. So that's the basic idea of word embeddings, and then these vectors somehow capture a lot of interesting information, both about the semantics. So in the first example, so you let, say, word2vec run on the entire English Wikipedia, and you get these vectors back. And if you look at some basic examples, so the classical examples. Man king minus man equals queen minus woman. And the model somehow captures a sense of gender or verb tense, or even slightly more complex relationships such as countries and their capitals, and all in an unsupervised way, which is obviously why word2vec and word embeddings in general are so popular. And then you can leverage this information as input to your deep neural nets for various tasks. So word embeddings have obviously become the sort of the de facto input layer in many NLP tasks, but they obviously have problems too. So some of these problems, so they can't handle unknown words and out of vocabulary words. So that's, I think, one of the most obvious issues. So if you haven't encountered the word before, you can't sort of generate a vector for it. And so if you're in a downstream task, you're sort of forced to use a randomized vector, which is obviously isn't great. And this can be particularly an issue in sparse and noisy domains like Twitter, where a word might have you might see a word only a couple of times, and so say it might get pruned if you're, say, using word2vec and you can't sort of have a meaningful representation for that word or phrase. The second issue is that there's no shared representation at subword level with word2vec. So for instance, when you and I encounter a word, a new word that we haven't seen before, we can somehow guess what it means based on, say, some morphological information. So for instance, if you see a word that ends in less, even we can sort of guess that it's probably an adjective and it's probably indicating lack of something. And thirdly, I think as we discuss, it's sort of in contradiction with our language independence requirements. And I think finally, if you have a model, if you have a downstream application or a downstream architecture that requires character-based models, you cannot really leverage pre-training or pre-trained word embeddings through word vector. And that's and so because of these reasons, we've come up with an enhancement to word2vec, which essentially creates embeddings based on the rawest form of input being bytes. And so the motivation here is to overcome some of the challenges that I just mentioned. So byte2vec is language independent because it's constructed from bytes. So it's a lot easier to actually have multilingual models. It's suitable for morphologically rich languages. It is able to deal with out-of-vocabulary words a lot better. Finally, it's easily pluggable into state-of-the-art neural net architectures, especially if you're taking, say, characters as input. And so the architect, and sorry, I forgot to mention this. This is a work by two of our great research scientists, Sebastian Ruder and Nicolas Péchu. And the architecture essentially looks like this. So we have a sentence like the deep learning model is, and then we convert that to a set of bytes. We create byte vectors from them, which are essentially of a very small vocabulary size of about 260. And then over that, we perform convolution and max pooling. We get orthographically sensitive byte-based word embeddings, and then we perform projection. We pass it through one or two highway layers, and then we get semantically sensitive byte-based word embeddings. And the whole thing is trained with a skip-gram objective. So in the end, you essentially get word embeddings for each of the words. Yeah, so that's byte2vec in a nutshell. We are opening the code as well as submitting a publication right now based on this. So I think in summary, one of the things to have in mind is obviously this transition from like rule-based and linguistics-based systems to classical machine learning to modern machine learning approaches and deep learning-based approaches. So I think, say, with a simple task like sentiment classification, we've almost had these three sort of distinct phases or eras, where initially we had like rule-based systems, and so say if you hate as, or if, I don't know, if you say awful as an adjective in a tweet, then that tweet must be negative. And then we had the second phase with like classical machine learning, so you would say these 10,000 tweets are positive and these 10,000 are negative, and then you would do some feature engineering and extract features, feed it to an SVM or a logistic regression model, and which is able to discriminate between the classes. And then I think the third generation is kind of what's happening right now with state-of-the-art deep learning approaches. You can go pretty far by training word embeddings on large corpuses of unannotated data, and then using distance supervision or any kind of weak signal to train your model, which is obviously much less supervised than both of the previous approaches. And then I think, secondly, there's language independence. So I think for such broad and high volume domains, such as Twitter and social media, whatever representational model we come up with, I think it must be able to deal with multiple languages. Only about a third of tweets are in English. So I think that's sort of a fundamental requirement of our current diverse fragmented world. And then finally, I'd like to reiterate that byte2vec can be an effective supplement to word2vec, and I think it will help us do better in noisier, sparser domains. And as I said, we're releasing a publication in the coming weeks, so please stay tuned. That's it. Any questions? Yep.
Sure. Can you, I don't know if you want to disclose any details, but can you talk a little bit about how the byte level encodings are actually folded into sort of the upper levels of the NLP processing chain?
Sure. So in terms of leveraging this, I think you can have two approaches. The first approach is to sort of pre-train word embeddings using the byte embeddings, and then feed those word embeddings to your downstream task. Or the second way to do it would be to sort of plug the decoder into your architecture. So if you have like CNN that takes character input, you can actually have the byte embeddings and then all the all of the stack on top that essentially allows you to fine-tune these embeddings at training time. So I think that you have two general ways to leverage this in downstream tasks. But I think from what we found, it works best in a multilingual setting where you pre-train the word embeddings first, get the word embeddings, and then feed it to your neural net.
And do you pre-train those character embeddings on a multilingual set, or
yes,
you just throw everything at it and you get a generalized representation and you use that in each one?
We currently use, well, I mean, I'm not sure if I can tell you this. No, sorry, I can't tell you that. Yep.
Have you visualized the convolutional filters that you have there? So for things like convolutions over text, those things usually pick up syllables as
right.
a common n-grams of characters, things like that. What's an n-gram in byte space?
Sure, I think, well, I mean, so we have a fixed window size of bytes in the input. So if we go back to the this, so we get the byte vectors, we perform the convolution, and then at this point, so we just try to get it in this shape, and after we perform convolution and max pooling, and then in terms of visualizing what's here, so an n-gram. I mean, yeah. So we don't have any n-gram. I think is. I mean, it's something that you use in a word context. A byte-based n-gram, I'm honestly not sure what it would look like.
I mean, I can imagine that you have UTF sort of prefixes for every character. Maybe I have no idea how UTF works, but I imagine that some of those convolutions would indicate prefixes for this is like the normal ASCII character, or this is like a Chinese character, or so
there's a language byte, so in the input.
So
yeah.
You know that's present in there. So
yeah.
There might be occurrences of bytes and that would then be picked up by convolutional filters. Another question is, but there's a really similar paper by Kim et al. That also take convolutions and then pass them through highway filters.
Yeah, the language modeling one.
Yeah. It's a character level. It's very similar. It's at byte level, and the architecture is very similar.
Sure.
And there they showed a really interesting thing at the highway level, right before the rise of the highway. Embeddings are sort of morphologically similar, so they look really similar. So while and whole, because they're only one part of it, really similar. But at the end of that highway level, things that are similar are semantically similar.
Sure. Yeah.
Do you guys have some sort of similar analogy?
Exactly. So we've observed the same thing. So with the tasks like nearest neighbors or nearest neighbors. Before, if you remove the highway layer, what you get is the similarities are almost entirely morphological. But then after adding those highway layers, somehow I don't have a good intuition for it, honestly. They start to get more and more semantically similar. So we run experiments with different numbers of highway layers, as well as instead of say running convolutions using an LSTM. I think the best results we've obtained so far are with 2 highway layers and convolutions. But I don't know why.
Yeah, I think that's common.
Sure.
To a great extent, does it happen quicker if you train on languages separately and then merge them later?
Sorry. So
if you train independent models on each language and then merge them later, do you send the gradient faster, or just do it all together?
Right. I don't know, to be honest, if it would be faster in terms of convergence. But yeah, since the base idea was to have something that can extend to more than one language, and then that was sort of the objective from the get-go. I think that's why we didn't run many experiments in a monolingual setting. And certainly no performance comparison between the two, as far as I know. Yeah. Thanks everyone.